August 17, 1943. The Mediterranean sun beat down on the rocky slopes near Messina, Sicily, as Oberleutnant Werner Hoffmann knelt beside the body of an American infantryman. The soldier had fallen during the chaotic American advance across the island, his backpack still strapped to his shoulders. Hoffmann's orders were clear. Capture any American radio equipment intact. Berlin wanted to know what the Allies were using. As Hoffmann carefully removed the 35-pound pack, something felt wrong. German infantry radios required 2 men to operate, one carrying the transmitter and receiver, another lugging the separate battery pack, connected by cable. Yet this American soldier had been operating alone, moving freely with his company. Inside the olive-drab case, Hoffmann discovered an 18-tube FM transceiver, complete with batteries, control unit, and 2 antenna sections, all integrated into a single backpack system that one man could carry and operate independently. The frequency dial showed channels from 40 to 48 megacycles. VHF band, the same range where German tank radios operated, but this was infantry equipment, designed for common soldiers. 2 days later, that captured radio sat on a workbench in a requisitioned villa outside Catania, where German signals intelligence maintained a forward technical evaluation unit. Hauptmann Klaus Dieter, a communications engineer who had designed components for the Wehrmacht's Torn-Fu radio series, began his examination. He had spent 5 years helping develop Germany's infantry radios, equipment he knew intimately. What he discovered in the next 72 hours would challenge everything German engineers believed about battlefield communications and what was possible with mass-produced military equipment. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how German engineers reacted to captured American radio equipment reveals not just a technological gap, but a fundamental difference in industrial philosophy. It's a story about frequency modulation versus amplitude modulation, about design for manufacturing versus craftsman assembly, about the collision between German technical excellence and American industrial capacity. Most importantly, it's a story about the moment German engineers began to understand that the war would not be won through superior engineering alone. To understand the shock Klaus Dieter experienced that August morning in Sicily, we must first understand the state of battlefield communications in 1943 and the fundamental differences between how Germany and America approached the problem of mobile infantry radio. Since the beginning of the war, the Wehrmacht had relied on the Torn-Fu series of backpack radios. Torn, short for tornister or knapsack, designated portable infantry equipment. The most common model, the Torn-Fu D2, operated in the VHF band from 33.8 to 38 megacycles. It transmitted 1.5 watts of power using amplitude modulation for voice and continuous wave for Morse code. Under ideal conditions with an elevated antenna, it could achieve 10 to 12 kilometers range using Morse code, or 4 to 5 kilometers using voice. But the Torn-Fu D2 required 2 soldiers to operate. One man carried the transmitter-receiver unit weighing approximately 15 kilograms. The second man carried the battery pack, weighing another 12 kilograms, along with the handset, Morse key, and accessories. A cable connected the 2 soldiers together. They could move, but not independently. This design reflected fundamental constraints in German radio engineering: the need for separate high-voltage batteries to power vacuum tubes, the bulk of AM circuit components, and the weight of lead-acid batteries that could sustain field operations. Every German infantry battalion had 4 Torn-Fu D2 radios to maintain communications between companies and battalion headquarters. The equipment worked reliably when properly maintained, but it had limitations that frustrated infantry commanders. The 2-man requirement reduced tactical flexibility. The AM modulation picked up interference from vehicle engines, electrical equipment, and atmospheric conditions. The limited range meant infantry companies advancing beyond 4 to 5 kilometers lost contact with battalion headquarters unless they stopped to extend relay antennas. German engineers understood these limitations. They had experimented with frequency modulation, which offered superior noise rejection and clearer voice transmission. But FM required significantly more complex circuits, precise frequency control, and specialized components that were difficult to manufacture in quantity. German industry in 1943 was focused on producing existing weapons in maximum quantities, not developing sophisticated new technologies for mass production. The decision had been made. Stick with AM for infantry radios, reserve FM for specialized applications where the added complexity could be justified. American radio development had followed a different path, driven by one engineer's determination to give infantry troops something better. In September 1940, Daniel Earl Noble walked into the Galvin Manufacturing Corporation in Chicago as the company's new director of research. Noble brought specific expertise that would prove crucial. He had designed and installed the nation's first statewide two-way FM radio communications system for the Connecticut State Police, completed earlier that same year. He understood what FM could do: static-free communication, resistance to electrical interference, and clarity that AM systems simply could not match. Noble arrived at Galvin Manufacturing at a moment when the U.S. military desperately needed better battlefield radios. The Army's existing portable infantry radios, the SCR-194 and 195, were notorious failures. They used primitive super-regenerative circuits operating on AM frequencies. Every vehicle engine, every electrical motor, every thunderstorm generated static that drowned out vital communications. The radios were so unreliable that many infantry officers preferred sending runners carrying messages by hand, even though runners could be killed or captured, even though messages might arrive too late. Galvin Manufacturing had achieved some success with the SCR-536, a handheld AM radio nicknamed the Handy Talkie. It was compact, crystal-controlled for frequency stability, and truly handheld, but its maximum effective range was approximately 1 mile under good conditions, useless for communications between companies and battalion headquarters several miles to the rear, useless for forward observers directing artillery fire from observation posts miles from the gun batteries. In early 1941, the Army Signal Corps contracted for development of a new portable infantry radio. The specifications called for AM technology, the safe, proven, conservative choice. When Noble learned of this decision, his response was immediate and risky. He told Army officers directly that developing an AM portable radio was a grave mistake. He argued forcefully that FM was the right technology for portable military radio, despite the Army's clear preference for familiar AM systems. Noble was asking busy military procurement officers to trust his technical judgment over their own institutional preferences. He was advocating for a more complex and potentially more expensive solution when the simpler option seemed adequate. He was staking his professional reputation on beliefs that many considered theoretical rather than practical, but Noble understood something that others had not fully grasped. Soldiers operating in the electromagnetically hostile environment of modern mechanized warfare needed communications that would work reliably despite massive electrical interference. They needed clear voice transmission at the limits of range, where the difference between understanding and confusion could mean the difference between coordinated action and catastrophic failure. The Army Signal Corps agreed to gamble on FM technology. In 1942, Galvin Manufacturing received a contract to develop a portable FM infantry radio, designated SCR-300. The specifications were demanding. The complete radio system could weigh no more than 35 pounds, had to be carried on one soldier's back, must operate in all weather conditions with waterproof construction, needed to provide reliable communications over at least 3 miles, and had to cover the 40 to 48 megacycle VHF band using frequency modulation with minimal crystals. Noble assembled an engineering team: Henrik Magnuski as principal RF engineer, Marion Bond, Lloyd Morris, and Bill Vogel. He gave them one message: the Signal Corps has placed a life-and-death priority on this program for the infantry. Soldiers' lives would depend on whether this radio worked reliably in combat. The engineering challenge was formidable. Frequency modulation required complex circuits that were difficult to stabilize. Vacuum tubes needed high-voltage power supplies. Batteries capable of sustained field operation added significant weight. Everything had to be ruggedized for combat conditions while remaining light enough for one soldier to carry. The entire system had to be simple enough for infantrymen with minimal technical training to operate reliably under fire. By spring 1942, the team had 2 working prototypes. For final testing, they chose an ambitious demonstration. Daniel Noble and a colleague stood 8 miles apart in the fields of Fort Knox, Kentucky. When Noble pressed the transmit button and spoke into the handset, his colleague 8 miles away heard every word with crystal clarity, free of static and interference. The Army had specified a minimum range of 3 miles. The prototype had just demonstrated more than double that distance. The Signal Corps officers present at Fort Knox that day were impressed enough to approve full-scale production. What they were witnessing was a radio that would give American infantry a decisive communications advantage. What they couldn't yet know was how that advantage would appear to German engineers examining the equipment after capturing it in combat. The SCR-300 that emerged from Motorola's production lines represented a leap forward in battlefield communications technology. The radio itself, designated BC-1000, was an 18-tube FM transceiver using a double superheterodyne receiver design. It incorporated automatic frequency control circuits that maintained stable operation without constant manual adjustment. German radios required operators to continuously adjust tuning to compensate for temperature drift and component aging. The American radio tuned itself. The frequency selector allowed operators to choose any of 41 channels across the 40 to 48 megacycle VHF band. A squelch circuit eliminated background noise when no transmission was received. The frequency calibration used a crystal-controlled oscillator with harmonics marked on the channel display, allowing precise tuning without external equipment. 2 antenna options were provided: a short 33-inch whip with an LC matching circuit for close-range communication, and a 10-foot, 8-inch half-wavelength antenna in 9 collapsible sections for maximum range. The transmitter produced a minimum of 300 milliwatts of carrier power. The receiver sensitivity was guaranteed at 4.5 microvolts minimum. These specifications promised reliable 3 to 5 mile range in varying terrain. The entire system with batteries weighed 35 pounds, exactly meeting the original specification, light enough for one soldier to carry and operate independently while moving with his unit. Production began in earnest during 1942. By the time Sicily was invaded in July 1943, nearly 50,000 SCR-300 units would be manufactured. The first units were transported by air for use in the invasion of Italy. Such was the priority placed on getting these radios to frontline troops. Now, we return to that requisitioned villa outside Catania in August 1943, where Hauptmann Klaus Dieter began his systematic examination of the captured American equipment. Dieter started with external inspection. The radio was housed in a sturdy steel case painted olive drab. Heavy rubber gaskets protected every seam and connector. The construction quality immediately struck him as exceptional. German military radios were well made, but this level of protection against water, dust, shock, and temperature extremes exceeded anything in Wehrmacht inventory. The case was designed for soldiers who would carry this equipment through rain, mud, river crossings, and jungle humidity without any expectation of gentle treatment. When Dieter opened the case and examined the internal construction, his first reaction was confusion, followed by growing unease. Everything inside was standardized, modular, designed for mass production. Every component was identical to specifications documented in the accompanying technical manual that had been captured with the radio. There were no hand adjustments, no technician marks indicating individual tuning during assembly, no variations that would require skilled labor. This was equipment designed to be built by semi-skilled workers in factories that could be replicated across an entire continent. German radio production required trained technicians to hand-tune circuits during assembly. Each radio was slightly different, requiring documentation of its specific adjustments. The American radio needed none of that. Any SCR-300 could be repaired using parts from any other SCR-300. Standardization and interchangeability at a level German industry had never achieved in military electronics. Dieter then examined the frequency control system. He expected to find simple, perhaps salvaged civilian components. Instead, he discovered precision quartz crystal oscillators, hermetically sealed in metal holders, each ground to tolerances measured in parts per million. The automatic frequency control circuit used these crystals to maintain rock-solid frequency stability across temperature variations and power supply fluctuations that would render German radios useless. But what truly shocked Dieter was discovering that this was standard equipment for ordinary infantry soldiers. This wasn't a radio for regimental commanders or special operations units where sophisticated equipment might be justified. This was the radio issued to infantry battalion signal sections, carried by private soldiers, operated by men who might have been farmers or factory workers 6 months earlier. The implications became clearer as Dieter conducted transmission tests over the following days. He set up the captured SCR-300 with its full 10-foot antenna and powered it from a German field generator. His assistant took a German Tornfude 2 radio 5 kilometers away to the east, near the coastal town of Asiriale. They would test both radios simultaneously under identical conditions to compare performance. At 1500 hours on August 19th, Dieter transmitted on the American radio. His assistant, 5 kilometers distant, reported receiving the transmission with perfect clarity. No static, no interference from nearby German vehicles, no atmospheric noise. The FM signal cut through everything. Then they reversed the test. The German Tornfude 2 transmitted from Asiriale. Dieter, listening on the German receiver, heard the message, but it was degraded by engine noise from Wehrmacht trucks passing nearby, overlaid with the characteristic hiss and pop of AM static. They increased the distance to 7 kilometers. The American radio still maintained clear communications. The German radio's voice transmission became marginal, difficult to understand without repeated transmissions. At 10 kilometers, the SCR-300 was still usable for voice, though beginning to fade. The Tornfude 2 at that range required switching to Morse code for reliable communication, and even then, the signal was weak. Dieter wrote in his initial assessment report that the American infantry radio represented a capability that exceeded German regimental-level equipment in both range and reliability, yet it was apparently issued down to battalion level, possibly even to company level based on the circumstances of its capture. The FM modulation provided interference immunity that made it practical in the electrically noisy environment of modern mechanized combat. Most concerning, the design and construction suggested mass production at a scale Germany could not match. That evening, Dieter discussed his findings with Oberst Friedrich Müller, commander of the Signals Intelligence Detachment. Müller had been a professor of electrical engineering before the war and understood the implications immediately. If American infantry companies could communicate reliably over 5 miles, while German companies struggled beyond 3 or 4 kilometers, American forces would maintain superior command and control. They could coordinate faster, adjust to changing situations more quickly, bring artillery and air support to bear with greater speed and accuracy. But the real concern was what this radio revealed about American industrial capacity. Müller pointed out that the technical manual captured with the radio indicated it was designated Radio Set SCR-300-A, suggesting there had been earlier versions, refinements, continuous improvement. The manual was professionally printed, comprehensive, designed for soldiers with minimal technical knowledge. Everything about this equipment suggested a mature production system, not an experimental prototype. If the Americans were equipping infantry battalions with radios this sophisticated, Müller asked, what were they giving to armored units, to artillery, to air forces? And more important, how many were they producing? Dieter had no answer to that question, but his examination of the radio's components provided disturbing clues. The vacuum tubes were standard types, manufactured to tight specifications, interchangeable, not specially made tubes that would require dedicated production facilities. The capacitors, resistors, and other components were military-grade, but using manufacturing techniques that suggested high-volume production. The crystal oscillators were the most telling. These were precision components that in Germany required laboratory work, skilled technicians, time-consuming grinding and testing. Here they appeared as standardized units, marked with specifications, sealed for reliability, installed as casually as light bulbs. Germany in 1943 was experiencing severe shortages of many materials critical for radio production. Quartz crystal for frequency control was particularly scarce. German radio designs minimized crystal use, often relying on less stable but more available variable capacitor tuning. The Americans apparently had enough precision quartz crystals to install automatic frequency control systems in infantry radios, equipment that might be lost or destroyed in any firefight. Over the next week, as Allied forces completed their conquest of Sicily, more captured American radio equipment reached German technical intelligence units. Additional SCR-300 radios were recovered, some damaged, some intact. Each one confirmed what Dieter had discovered. This was standardized equipment, mass-produced, built to identical specifications. Serial numbers on different units showed they had been manufactured months apart, yet the components were completely interchangeable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German signals intelligence also intercepted American radio traffic using the SCR-300 during operations in Sicily. What they heard was revealing. American infantry units communicated freely, frequently, coordinating movements with a casualness that suggested they had complete confidence in their communications. German doctrine emphasized radio silence to avoid direction finding, transmitting only when necessary because radio communications were assumed to be vulnerable and unreliable. American forces seemed to operate under different assumptions. Their radios were so reliable, so resistant to interference, that they used them constantly. This difference in radio doctrine reflected deeper differences in military organization. German infantry tactics emphasized written orders, runners, and physical coordination because radio communications were limited. American tactics increasingly relied on radio as the primary means of command and control because their equipment made it practical. Superior communications allowed American forces to coordinate combined arms operations more effectively, adjust to changing situations faster, and maintain the initiative even when German forces might have tactical advantages in other areas. The captured SCR-300 was eventually transported to Germany for more detailed technical analysis. It arrived at the Army High Command's Signals Research Facility outside Berlin in September 1943. Dr. Heinrich Weber, director of the Radio Development Section, supervised the comprehensive evaluation. Weber had spent his career in radio engineering. He held patents for several innovations in AM receiver design and had consulted on the development of Germany's Fugue series of tank radios. He approached the American equipment with the skeptical confidence of someone who had seen many foreign radios and understood German equipment to be among the world's finest. His team disassembled the SCR-300 completely. Every component was catalogued, measured, tested. They traced circuit designs, analyzed the frequency modulation system, examined the automatic frequency control mechanism. They tested the radio's performance under various conditions, simulated field operations, measured sensitivity and selectivity, evaluated the transmitter's spectral purity. The technical evaluation took 3 weeks. Weber's final report to Wehrmacht High Command ran to 47 pages, including detailed circuit diagrams, performance measurements, and strategic assessments. The conclusions were stark and troubling. The report confirmed that the American infantry radio used frequency modulation technology superior to German AM systems for battlefield applications. The FM system provided approximately 10 to 15 decibels better signal-to-noise ratio in the presence of electrical interference compared to German AM equipment. This meant American radios could maintain communications in environments where German radios would be unusable. The automatic frequency control system using precision crystal oscillators eliminated the need for constant manual tuning and provided frequency stability that German radios could not match without dedicated operator attention. The construction quality and ruggedization exceeded German military standards. The radio was designed to function after being dropped, submerged in water, exposed to temperature extremes from -30 to +60 degrees Celsius, operated continuously for extended periods without maintenance beyond battery replacement. German radios required more frequent maintenance and were more susceptible to failure under harsh field conditions. But Weber's most significant finding was about manufacturability. Every aspect of the SCR-300's design reflected an obsession with mass production. Components were standardized for interchangeability. Assembly required no specialized skills beyond careful attention to instructions. Testing and calibration were built into the design through self-adjusting circuits and calibration crystals. Quality control could be achieved through go-no-go testing rather than skilled technician evaluation. Weber calculated that a factory with semi-skilled workers could produce SCR-300 radios at perhaps 5 to 10 times the rate that German factories produced Torn-Fu radios, even accounting for the greater complexity of the FM design. The American emphasis on design for manufacturing meant that their more sophisticated radio could actually be produced faster and cheaper than Germany's simpler equipment once the production system was established. The strategic implications section of Weber's report made for grim reading at Wehrmacht High Command. If the Americans could produce sophisticated FM infantry radios in quantity, they possessed industrial capacity and technical capability that exceeded German estimates. The radio represented not just superior equipment, but a superior industrial philosophy. Design for mass production. Build quality into the process. Create systems that don't require skilled operators or maintenance technicians. This approach allowed America to field advanced equipment in quantities that German craftsman-based production methods could never match. A technologically superior German radio that could only be produced in limited numbers would be overwhelmed by slightly less sophisticated American radios produced in unlimited quantities. The side that could build more equipment, faster, with less skilled labor, would ultimately prevail regardless of theoretical technical superiority. Weber noted in his report that Germany faced a fundamental choice: attempt to copy American production methods, which would require complete reorganization of manufacturing systems and might not be achievable with available resources and industrial infrastructure, or accept that Germany could not match American production quantities and develop tactics and strategies that worked around this limitation. The reality, though Weber did not state it explicitly in his official report, was that neither option was viable in 1943. German industry was fully committed to producing existing weapons. The resources and time required to reorganize for American-style mass production didn't exist, and no tactical brilliance could overcome a 3-to-1 or 5-to-1 numerical disadvantage in critical equipment sustained across months and years of combat. Wehrmacht High Command filed Weber's report with other assessments of captured Allied equipment. The information was classified, distributed only to senior officers and technical specialists. Some commanders took the warnings seriously and adjusted their tactical planning accordingly. Others dismissed the concerns, arguing that German technical expertise and superior training would overcome any Allied material advantages. But in the field, German soldiers increasingly encountered American units with communications capabilities that exceeded their own. American infantry companies maintained constant contact with battalion headquarters. American artillery forward observers called fire missions with speed and precision that German observers could not match. American armored units coordinated with infantry support more effectively than German combined arms doctrine anticipated. The communications advantage provided by the SCR-300 and similar FM radio equipment was not by itself decisive in any single battle, but sustained across thousands of engagements from Italy to France to Germany, it contributed materially to Allied victory. Superior communications meant better coordination, faster response to changing situations, more effective use of firepower, and reduced vulnerability to surprise or encirclement. By 1944, as Allied forces invaded Normandy and advanced across France, the SCR-300 had become standard equipment in American and Allied infantry units. Nearly 50,000 had been produced. They served in every theatre where American forces fought. From the volcanic islands of the Pacific to the jungles of New Guinea, from the mountains of Italy to the hedgerows of Normandy, from the forests of the Ardennes to the final drive across Germany, the radio proved itself in the Battle of the Bulge during December 1944, when German forces launched their surprise offensive through the Ardennes. In the initial chaos, when American units were surrounded, cut off, scattered across frozen forests, the SCR-300 allowed isolated forces to maintain contact, coordinate defensive positions, and call for support. The radio's reliability in cold weather and its ability to function despite electromagnetic interference from vehicle engines and weapons fire helped American forces maintain cohesion during the critical first days of the battle. Some military historians have argued that the SCR-300 was among the most important pieces of communications equipment employed in the European theatre. That assessment may be debatable, but what is certain is that the radio gave American forces a significant tactical advantage that German forces never closed. The story of German engineers examining the captured SCR-300 is ultimately about industrial warfare and the revolution in manufacturing that occurred in America during World War II. It's about the transformation of warfare from an activity determined primarily by tactics, training, and courage to one determined by industrial capacity, technological sophistication, and manufacturing efficiency. The frequency modulation technology that so impressed German engineers examining the SCR-300 wasn't magic. It was established radio theory that German engineers understood perfectly well. What they couldn't match was the American ability to translate that theory into practical equipment that could be mass-produced by semi-skilled workers in quantities large enough to equip an entire army. This capability developed for radio equipment extended to every aspect of American military production. Tanks, aircraft, artillery, trucks, ammunition, all produced to standardized specifications in quantities that overwhelmed Axis forces, despite whatever tactical or technical advantages they might have possessed in individual engagements. Klaus Dieter, the signals officer who first examined the captured SCR-300 in Sicily, survived the war. In 1946, he returned to civilian life as an electrical engineer in Munich. He spent his post-war career helping rebuild German telecommunications infrastructure, applying lessons learned from examining American equipment about the importance of standardization, interchangeability, and design for manufacturability. In a 1972 interview for a German technical magazine, Dieter reflected on that August day in 1943 when he first opened the case of the captured American infantry radio. He said that he knew immediately, looking at the design and construction, that Germany would lose the war, not because of any single battle or campaign, but because the radio revealed an industrial capacity that Germany simply could not match. The Americans had industrialized everything from radio crystals to entire armies, applying the same mass production philosophy that built automobiles and refrigerators to military equipment. Germany, Dieter said, tried to fight an industrial war with craftsman methods. It wasn't that German technology was inferior. In many areas, German theoretical knowledge exceeded American, but theory doesn't win wars. Production capacity wins wars. The side that can build more equipment faster with less skilled labor will eventually overwhelm any opponent, no matter how brave or well-trained. Heinrich Weber, who directed the detailed technical evaluation in Berlin, did not survive the war. He remained in Berlin through the final Soviet assault in April 1945, conducting technical assessments and destroying classified documents until ordered to evacuate. His final report, dated April 23, 1945, assessed the latest American radar equipment and concluded that American electronics production had advanced so far beyond German capabilities that any hope of closing the gap was futile. Weber died on April 28 during the evacuation, killed when Soviet artillery struck the convoy carrying technical personnel westward. His papers, recovered after the war by American technical intelligence teams, included personal notes expressing frustration that his reports documenting American industrial superiority had been filed away rather than prompting meaningful changes in German production strategy. He wrote that German leadership seemed unable to accept that technical excellence without production capacity was meaningless in modern industrial warfare. The SCR-300 itself continued in service after World War II. It saw action in the Korean War, where its reliability in cold weather and mountainous terrain again proved valuable. Eventually, lighter transistorized radios like the PRC-10 and later the PRC-25 replaced it, but these newer radios built directly on the FM principles that the SCR-300 had proven in combat. The fundamental design philosophy embodied in the SCR-300, design for mass production, build in quality, standardize for interchangeability, became the foundation of modern military equipment development. The principles visible in the American radio in 1943 now govern military procurement worldwide. Every modern infantry radio, from the sophisticated software-defined radios used by American forces today to the simpler equipment used by militaries with fewer resources, reflects the lessons learned from the SCR-300. The story that began with a German signals officer examining captured equipment in Sicily in August 1943 concluded with the complete transformation of how nations prepare for and conduct warfare. The radio that Klaus Dieter held in his hands that day, studying its circuits and construction with growing unease, represented the future of military technology. Mass-produced precision equipment, designed for ease of manufacture and operation, produced in quantities that made individual technical superiority irrelevant. German engineers, who examined American radio equipment during the war, understood this transformation as it happened. Their reports documented not just technical specifications, but the end of one kind of warfare and the beginning of another. They witnessed, analyzed, and reported the future of conflict, that their warnings went unheeded in Berlin, that German leadership proved unable or unwilling to adapt to industrial reality, did not diminish the accuracy of their assessments. Today, the principles they identified remain fundamental to military equipment development. Mass production of precision components, industrial automation, standardization for interchangeability, design for manufacturability, these concepts govern every high-technology military system. The direct line runs from frequency modulation radios produced in American factories in 1943 to the sophisticated communications equipment used by military forces worldwide in the 21st century. The industrial philosophy remains the same, only the scale and sophistication have changed. The SCR-300 backpack radio weighed 35 pounds, used 18 vacuum tubes, operated on batteries that lasted perhaps 40 hours, and provided reliable voice communications over 3 to 5 miles. By modern standards, it was primitive. Today's infantry radios weigh a fraction as much, use digital encryption, operate on multiple frequency bands simultaneously, integrate with satellite communications and data networks, and provide capabilities that would have seemed impossible in 1943. But the fundamental principle remains unchanged. The side with greater industrial capacity to produce advanced equipment in overwhelming quantities will ultimately prevail. The Americans proved that principle between 1941 and 1945, producing nearly 50,000 SCR-300 radios, along with millions of other pieces of military equipment. The world has been adapting to its implications ever since. In an age of software-defined radios, satellite communications, and computer-controlled warfare, the fundamental truth that German engineers discovered examining captured American equipment in Sicily remains relevant. Industrial capacity, properly organized and directed, determines the outcome of modern conflicts. Without the ability to produce high-technology equipment in sufficient quantities, no amount of tactical skill, technical innovation, or individual courage can achieve victory. The German engineers who examined the SCR-300 in 1943 were not just studying a communications device. They were witnessing the future of warfare, the moment when victory stopped being determined primarily by battlefield prowess and started being determined by factory output. Their detailed reports, classified and filed away during the war, eventually became historical documents that explained not just why Germany lost, but how industrial capacity determines the outcome of modern conflicts. The conclusion, written in technical language but unmistakable in meaning, was that Germany had challenged the world's greatest industrial power with inadequate manufacturing capacity. The American infantry radio, with its FM modulation, automatic frequency control, precision components, and mass production design, told the entire story in a 35-pound package that any infantryman could carry. Industrial warfare demands industrial capacity. Without it, no amount of technical brilliance can achieve victory. That lesson, learned by German engineers examining American radio equipment in underground laboratories and requisitioned villas across occupied Europe, remains as relevant in the 21st century as it was in 1943. The names have changed, the technologies have advanced beyond recognition, but the fundamental principle endures. In modern warfare, industrial capacity to produce advanced technology in quantity determines outcomes more surely than any other factor. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. December 17, 1944. The Ardennes Forest, Belgium. Corporal Heinrich Müller pressed himself against the frozen earth, his carabiner 98K gripped in trembling hands. The morning fog clung to the pine trees like a burial shroud. Somewhere ahead, American positions waited in the darkness. Müller had been told these Americans were green replacements, exhausted from weeks of defensive fighting, low on ammunition and morale. What happened in the next 60 seconds would shatter everything Müller believed about American infantry. The attack order came, whispered down the line. Müller rose with his squad and advanced through the snow. 30 meters, 20 meters. Then the Americans opened fire. The sound was unlike anything in Müller's 3 years of combat experience. Not the measured crack-pause crack of bolt-action rifles he knew from the Eastern Front. This was continuous, relentless, a wall of semi-automatic fire that didn't stop. While Müller worked his bolt frantically, ejecting spent casings, chambering fresh rounds, breaking his aim with every shot, the American riflemen opposite him simply pulled their triggers. 8 rounds. Reload. 8 more rounds. The mathematics of survival had shifted catastrophically in America's favor, and German soldiers across every theater of World War II were learning this brutal lesson one firefight at a time. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how America fielded the world's only standard-issue semi-automatic rifle, while Germany clung to bolt-action technology, begins not on battlefields, but in the workshop of a self-taught Canadian immigrant who would revolutionize infantry combat. January 1st, 1888. Saint-Rémy, Quebec, Canada. Jean-Baptiste Garand entered the world on a modest farm 17 miles south of Montreal. Nothing about his humble origins suggested he would one day create what General George Patton would call the greatest battle implement ever devised. At 11 years old, young Jean moved with his family to rural Connecticut when his father abandoned farming for textile mill work. By age 12, the boy swept floors in a mill in Jewett City, but young Garand was fascinated by the machinery surrounding him. During breaks, he studied the mechanical looms, the steam engines, the precision gears that transformed raw cotton into finished cloth. This wasn't mere curiosity, this was the beginning of an education that would change warfare. By 18, Garand worked as a machinist. His natural aptitude led him to tool and gauge making, skills requiring both mathematical precision and artistic intuition. He took correspondence courses at night, teaching himself engineering principles most men learned only in universities. In 1916, at 28 years old, Garand turned his attention to firearms design. He submitted plans for a semi-automatic rifle to the United States Navy. 2 years later, the Navy was impressed enough to request he continue his work at the Bureau of Standards in Washington. After 18 months, Springfield Armory in Massachusetts offered him a position as a design engineer. What Garand found at Springfield shocked him. The legendary armory, which had given its name to the Springfield rifles equipping American forces in World War I, was hopelessly outdated. During the Great War, Springfield produced only 265,000 rifles, nowhere near enough for an army that grew from 200,000 to 4 million men. Another 47,000 came from Rock Island Arsenal. The massive shortfall forced America to arm hundreds of thousands of soldiers with British Enfield rifles manufactured under license by Remington and Winchester. The Springfield Model 1903 was a superb rifle, accurate and reliable, but it was designed to be hand-fitted by skilled armourers working at leisurely peacetime pace. Modern warfare demanded weapons that could be mass-produced quickly by semi-skilled workers using machine tools. Garand recognized that the next war would be won by the nation that could arm its soldiers fastest with the most effective weapons. The rifle he envisioned would fire every time the operator pulled the trigger, without requiring manual cycling of a bolt between shots. This semi-automatic operation would more than double the sustained rate of fire compared to bolt-action designs. It would allow soldiers to maintain their shooting position and sight picture between rounds. Most importantly, it would shift the balance of firepower decisively toward forces equipped with such weapons. Garand's path to success was anything but direct. His first designs used primer actuation, where the force of the primer explosion cycled the action. This proved unreliable in field conditions. He switched to gas operation, tapping propellant gases from the fired cartridge to power the mechanism. In 1929, his design won Army acceptance trials. Victory seemed certain. Then politics intervened with devastating effect. General Douglas MacArthur, Army Chief of Staff, insisted the rifle use the existing .30-06 Springfield cartridge rather than the newer .276 Pedersen round for which Garand had optimized his design. MacArthur's reasoning was purely economic. The Army had millions of rounds of .30-06 ammunition in storage. Starting fresh with a new caliber would cost millions of dollars and delay deployment for years America could not afford. Garand returned to his workshop and redesigned the entire rifle for the heavier, more powerful .30-06 cartridge. The process consumed 3 years of painstaking work. On August 3, 1933, his redesigned rifle received official designation as the United States Rifle Caliber 30 M1. On January 9, 1936, the Army adopted it as the new standard infantry weapon. The first production M1 Garand was successfully proof-fired, function-fired, and fired for accuracy on July 21, 1937. Production began that September at a rate of 10 rifles per day. By January 1940, Springfield Armory produced 100 per day, but this was nowhere near enough for a nation watching Europe descend into mechanized warfare. On September 20, 1939, the same month Germany invaded Poland, Winchester Repeating Arms received a contract to manufacture M1 Garands. The company was less than enthusiastic about the prospect. Winchester engineers considered the Garand too complex, too expensive to produce using mass production techniques. Relations between Winchester and Springfield Armory personnel became openly hostile, with each side accusing the other of incompetence and unrealistic expectations. Despite the friction between manufacturers, both facilities ramped up production as war clouds gathered over the Atlantic. By December 7, 1941, when Japan attacked Pearl Harbor, American factories were producing rifles at unprecedented rates. The M1 Garand became an absolute top priority overnight. January 1942 saw Springfield Armory producing 1,130 Garands per day. Production peaked in January 1944, when Springfield alone manufactured 122,000 rifles in a single month. This translated to 3,936 rifles per day, or 164 rifles every hour of every day. Winchester added another 513,000 rifles between December 1940 and June 1945. By war's end in August 1945, over 4 million M1 Garands had been produced. The United States stood as the only major power to field a semi-automatic rifle as standard infantry equipment. Every other army, British, German, Soviet, Japanese, Italian, relied primarily on bolt-action designs developed decades earlier. The tactical implications of this disparity cannot be overstated. Understanding the advantage requires examining the mechanical reality of both weapons. A rifleman with a bolt-action rifle must perform multiple steps between each shot. Pull the bolt handle upward and rearward, ejecting the spent cartridge. Push the bolt forward, chambering a new round from the internal magazine. Push the bolt handle downward, locking it in place. Raise the rifle back to shooting position. Reacquire the target through the sights. Aim, fire. The entire cycle consumes 4 to 6 seconds for a trained soldier under ideal conditions, longer under combat stress when hands shake and exhaustion sets in. The M1 Garand eliminated most of these steps through elegant mechanical design. The soldier pulls the trigger. The rifle fires. Gas pressure from the fired cartridge diverts through a port in the barrel into a cylinder below. This gas drives a piston that cycles the action automatically. The bolt opens. The spent case ejects. A new round chambers from the 8-round en bloc clip. The bolt locks. Total time, 1/5 of a second. The rifle's action remains closed between shots, maintaining precise barrel-to-sight alignment. Accuracy does not suffer despite the rapid-fire capability. Testing at Springfield Armory demonstrated the M1 could maintain 4 minutes of angle groups, meaning 4 inches of spread at 100 yards. Many production rifles performed significantly better than this standard. The official U.S. Army aimed rate of fire for the M1 Garand was 24 rounds per minute under combat conditions. Experienced soldiers in favorable positions could achieve 40 to 50 aimed rounds per minute. Compare this to bolt-action rifles. The German Karabiner 98K, firing the powerful 7.92 by 57 mm Mauser cartridge from a 5-round internal magazine, managed approximately 15 aimed rounds per minute from highly trained soldiers. Under realistic combat conditions, accounting for the stress of incoming fire and the need to reload from stripper clips every 5 rounds, this rate dropped to 10 to 12 rounds per minute. The British Lee Enfield, with its 10-round magazine and famously smooth bolt action, was the fastest bolt-action rifle ever produced. British soldiers trained extensively in the Mad Minute drill could achieve 25 to 30 rounds per minute in short bursts under ideal range conditions. But sustained combat fire from the Lee Enfield averaged 15 rounds per minute. Even Britain's fastest bolt-action rifle could not match America's semi-automatic standard. The firepower mathematics told a stark story. In a 3-minute engagement, a German soldier with a Kar-98K firing at maximum sustainable rate would deliver 30 to 45 aimed rounds. An American soldier with an M1 Garand would deliver 72 to 150 rounds in the same period. The American maintained consistent aim throughout. The German broke his sight picture with every bolt cycle, interrupting the rhythm of aimed fire. Most critically, the American's rifle performed this cycling automatically, while the German performed it manually, consuming precious seconds that meant the difference between suppressing the enemy and being suppressed. But Germany possessed some of the world's finest weapons designers and most advanced manufacturing capabilities. Why did the Wehrmacht enter World War II armed primarily with a bolt-action rifle that differed only incrementally from designs used in World War I? The answer reveals profound differences in military doctrine, industrial capacity, and strategic calculation. The Karabiner 98K, adopted on June 21, 1935, represented the pinnacle of bolt-action rifle development. Mauser's design was legendary for good reason. The rifle was accurate out to 550 yards with iron sights, reliable in mud, dust, and frozen conditions, simple enough for conscripts to maintain with minimal instruction. It embodied everything a military rifle should be, according to German military thinking rooted in Prussian tradition. The Kar-98K fired the powerful 7.92 by 57 mm Mauser cartridge, capable of penetrating substantial cover. In trained hands, the weapon had conquered Poland, France, the Low Countries, Norway, Denmark, and driven deep into the Soviet Union. German military doctrine emphasized aimed fire from prepared defensive positions. Infantry training stressed the importance of each round being carefully placed. Marksmanship was a point of pride. A skilled German soldier working his bolt with practiced efficiency seemed adequate when facing Polish, French, and British troops armed with similar bolt-action weapons. The British Lee Enfield, with its larger 10-round magazine, could fire somewhat faster, but German officers considered this a questionable trade-off against precision and tactical discipline. Furthermore, German doctrine relied heavily on squad automatic weapons for suppressive fire. The MG-34 and later MG-42 machine guns provided devastating firepower at the squad level. In German tactical thinking, the rifleman's role was to deliver precise aimed shots, while the machine gunner suppressed the enemy. This division of labor seemed logical given the technology available. Germany did experiment with semi-automatic rifles. The Gewehr 41 and Gewehr 43 entered limited production during the war, but these rifles never achieved the reliability or manufacturing efficiency needed for mass deployment. Complex mechanisms jammed in field conditions. Production costs were prohibitive when resources were desperately needed elsewhere. The Kar-98K remained simpler to manufacture, easier to maintain, more reliable under terrible conditions. By the time German commanders fully grasped the tactical implications of America's semi-automatic advantage, it was far too late to retool the entire German small arms industry. When American forces entered major combat operations in North Africa in November 1942 during Operation Torch, German intelligence had prepared assessments of American equipment and tactics. These reports painted a picture of industrial abundance but military inexperience. American infantry, the assessments claimed, relied too heavily on firepower and too little on tactical skill and individual soldier quality. The M1 Garand appeared in these intelligence reports as a semi-automatic rifle of interest, but not particular concern or alarm. German analysts noted its 8-round capacity and self-loading mechanism, but pointed out it was heavier than the Kar-98K at approximately 9.5 pounds compared to 8.2 pounds. The general assessment concluded that while the M1 offered higher volume of fire, it supposedly sacrificed the accuracy and reliability inherent in simpler bolt-action mechanisms. This assessment would prove catastrophically wrong. American forces had been using the M1 Garand in combat since December 8, 1941, when Japanese forces invaded the Philippines the morning after Pearl Harbor. M1 rifles shipped between August and November 1941 had equipped the U.S. Army's Philippine Division and elite Philippine Scouts. These soldiers used their Garands effectively enough that Japanese troops reportedly believed they faced machine gun fire during defensive actions. General Douglas MacArthur cabled Washington in February 1942, praising the rifle's performance in the dust and dirt of foxhole fighting on Bataan. By the time German forces faced Americans in North Africa, the M1 Garand had proven itself through nearly a year of brutal jungle combat against determined Japanese infantry. The reality encountered on North African plains shattered German assumptions with brutal efficiency. German units established defensive positions, expecting to stop American advances with disciplined aimed fire, as they had stopped so many attacks before. When Americans assaulted these positions, the volume of return fire was overwhelming. Not machine gun fire, which Germans expected and knew how to handle through tactical training. This was rifle fire, continuous, sustained rifle fire that didn't pause. German soldiers would fire, work the bolt, reacquire the target, fire again, perhaps 15 rounds per minute from the best trained soldiers. But each American rifleman opposite them was firing 30 to 40 rounds per minute, maintaining accurate fire throughout. Germans could not suppress them with bolt-action rifles. Every time German soldiers raised their heads to acquire targets and fire, multiple American rounds came back immediately from semi-automatic rifles that never stopped shooting. The mathematics were undeniable and horrifying. In a 2-minute engagement, a German soldier with a Kar-98K might fire 30 aimed rounds if he was exceptionally well trained, and the tactical situation permitted sustained fire. An American with an M1 Garand could fire 80 rounds in the same period with less physical effort. More critically, the German soldier had to break his sight picture, work the bolt, reacquire his target, and fire with every single shot. The American simply pulled the trigger 8 times in rapid succession, his aim barely disturbed by the rifle's modest recoil, then loaded a fresh en-bloc clip in seconds and continued firing. The M1 Garand's semi-automatic operation relied on a gas-operated system of elegant simplicity. As a round fired, propellant gases were diverted through a port in the barrel into a cylinder positioned below. This gas drove a piston attached to an operating rod. The rod pushed the bolt rearward, ejecting the spent cartridge and compressing a recoil spring. The spring then drove the operating rod forward, chambering a new round from the en-bloc clip and locking the bolt closed. The entire mechanical cycle occurred in a fraction of a second. The rifle's action remained closed between shots, maintaining consistent barrel-to-sight alignment critical for accuracy. Extensive testing demonstrated the M1 maintained excellent precision despite its rapid-fire capability. General George S. Patton, in a letter dated January 26, 1945, to Major General Levin H. Campbell, Jr., Chief of Ordnance, wrote, "In my opinion, the M1 rifle is the greatest battle implement ever devised." This was not hyperbole from a general known for dramatic pronouncements. Patton understood with absolute clarity that the rifle had fundamentally changed the nature of infantry combat. A soldier armed with an M1 Garand possessed firepower equivalent to multiple riflemen with bolt-action weapons without sacrificing accuracy, reliability, or effective range. By mid-1943, the United States Army was equipping entire divisions with M1 Garands at a pace no other nation could match. During World War II, from 1937 through 1945, approximately 4,400,000 M1 rifles were manufactured. Springfield Armory in Massachusetts produced 3,526,922 rifles. Winchester Repeating Arms in Connecticut manufactured 513,880 additional units. Production reached such extraordinary levels that by D-Day in June 1944, virtually every American rifleman storming the beaches of Normandy carried an M1 Garand. This represented an unprecedented achievement in military logistics and industrial mobilization. An entire military force numbering in the millions was armed with semi-automatic rifles, while their opponents still carried bolt-action weapons designed before World War I. The M1 Garand's technical specifications revealed the engineering excellence behind its combat effectiveness. The rifle fired the .30-06 Springfield cartridge, a powerful round that had served American forces since 1906. The cartridge propelled a 150-grain bullet at approximately 2,800 feet per second, delivering substantial energy at extended ranges well beyond 500 yards. The rifle fed from an 8-round en-bloc clip, a metal clip inserted directly into the rifle's action from above. When the last round fired, the clip automatically ejected with a distinctive metallic ping that became one of the war's most recognizable sounds. While some soldiers worried this sound might alert enemies to an empty rifle, combat veterans universally reported that battle noise made the ping inaudible beyond a few yards. The thunder of artillery, the rattle of machine guns, the explosions of grenades, and the screams of wounded men drowned out such subtle mechanical sounds completely. The rifle measured 43.6 inches in overall length and weighed 9.5 pounds unloaded. This made it slightly heavier than the German Kar-98K at 8.2 pounds or the Soviet Mosin Nagant at 8.8 pounds. But the additional weight proved advantageous, absorbing recoil and providing stability for accurate rapid fire. The M1's walnut stock and parkerized metal finish gave it a distinctive appearance that became synonymous with American infantry throughout the war. The rifle's reliability under terrible conditions earned soldiers' trust. It functioned in the desert heat of North Africa, where temperatures exceeded 120 degrees Fahrenheit and sand infiltrated everything. It performed in the freezing forests of the Ardennes during the Battle of the Bulge, where temperatures plunged below zero and soldiers fought with frostbitten fingers. It worked in the humid jungles of the Pacific, where constant moisture rusted metal and rotted wood within days. The M1 Garand kept firing when soldiers needed it most, in conditions that would disable more delicate mechanisms. The story of how John Garand created this revolutionary weapon reveals the power of self-education and persistence. Born Jean-Baptiste Garand in rural Quebec, he received minimal formal education before his family immigrated to Connecticut in 1899. Working in textile mills as a child, he studied machinery with intense fascination. While other boys played, young Garand observed mechanical principles in action, teaching himself engineering through observation and experimentation. This self-taught approach would prove crucial to his later success. Unlike formally trained engineers who learned established methods at universities, Garand thought about mechanical problems from first principles. He wasn't constrained by conventional wisdom about what could or couldn't work. When he encountered design obstacles, he invented novel solutions rather than accepting limitations. In 1916, Garand submitted his first firearms design to the U.S. Navy. The Navy recognized his talent and brought him to Washington to continue development. By 1919, Springfield Armory offered him a permanent position. Garand would spend the next 34 years at Springfield, refining his rifle design through countless iterations. His early prototypes used primer actuation, where the primer's explosion provided energy to cycle the action. Testing revealed this approach lacked reliability. Garand switched to gas operation, bleeding propellant gases from the barrel to power the cycling mechanism. Early gas trap designs, which captured gases at the muzzle, proved problematic. Garand simplified to a gas port system tapping gases partway down the barrel. This design proved far more reliable and became the basis for the production M1. The rifle underwent extensive testing at Aberdeen Proving Ground and Springfield Armory throughout the early 1930s. Problems were identified and corrected systematically. The gas system was refined. The trigger mechanism was improved for a cleaner, crisper pull. The stock design was optimized for better ergonomics and durability. Every component was tested to destruction and redesigned as necessary. On January 9, 1936, the rifle was officially adopted as the United States Rifle Caliber 30 M1. Initial production was deliberately slow, with only a few thousand rifles manufactured in 1937 and 1938. Production accelerated dramatically as war approached Europe, reaching 600 rifles per day by January 1941. The M1 Garand served American forces through World War II, the Korean War, and into the early Vietnam years with distinction. It was not officially replaced as the standard service rifle until the M14 was adopted in 1957. The M14 was designated as the official replacement on March 26, 1958, with first deliveries to combat units beginning July 1959. Full transition across all regular Army units took until 1961. Even then, M1 Garands remained in service with Reserve and National Guard units well into the 1970s, a testament to the design's enduring effectiveness and reliability. The psychological impact of the M1 Garand on German soldiers manifested in profound and demoralizing ways. The weapon represented technological superiority that contradicted everything they had been taught about American military capabilities through years of Nazi propaganda. German soldiers had been conditioned by relentless propaganda to believe in Germanic technological and tactical superiority over all opponents. When individual German infantrymen, properly equipped and rigorously trained in Prussian military tradition, found themselves consistently unable to win firefights against individual American infantrymen, the carefully constructed myth of superiority collapsed. The experience was psychologically devastating for soldiers whose entire worldview rested on assumptions of German excellence. After World War II ended, detailed operational studies of small unit actions consistently showed American infantry inflicting disproportionate casualties in firefights relative to force ratios. The rifle each soldier carried made measurable, quantifiable difference in combat effectiveness that statisticians could document. American casualties from German rifle fire were proportionally lower than casualties German forces suffered from American rifle fire, another clear indicator of the M1's combat superiority. German attempts to compensate through superior tactics, better positioning, and exploitation of terrain worked only partially and temporarily. Tactical excellence could offset technological disadvantage to some degree, but eventually the sheer volume of accurate aimed fire from American infantry would find targets, suppress defensive positions, and enable American maneuver elements to close with and destroy German positions through combined arms coordination. The M1 Garand's legacy extends far beyond World War II into modern firearms development and military doctrine. The fundamental principle it demonstrated, that infantry benefit enormously from self-loading rifles that increase their rate of fire without sacrificing accuracy, became foundational to all post-war weapon development worldwide. Every modern infantry rifle, from the Soviet AK-47 to the American M16 to current assault rifles used by military forces globally, owes conceptual debt to the M1 Garand. It proved conclusively that semi-automatic operation was not just feasible for military service rifles, but absolutely essential for modern warfare. The story of German infantry encountering American forces armed with M1 Garands across multiple theaters represents a historical moment when technological advantage met traditional military excellence and demonstrated unambiguously that superior technology matters profoundly in combat outcomes. German infantry training, tactical doctrine, and individual soldier quality were excellent by any objective measure. German soldiers were among the best trained, most disciplined infantry in World War II. But excellence with inferior weapons produces inferior results against competent opponents with superior weapons. This is an uncomfortable truth that militaries throughout history have learned repeatedly at terrible cost. The M1 Garand gave American infantrymen a tool that allowed them to fight effectively, even when outnumbered, to win firefights, even when facing veteran troops with years of combat experience, and to advance against fortified positions that should have been nearly impregnable to infantry assault. From the Philippines to North Africa, from Sicily to Normandy, from the hedgerows of France to the Rhine River crossing, the M1 Garand served faithfully and effectively throughout the war. It earned its towering reputation as one of the finest military rifles ever designed through performance in the crucible of combat. General Patton's famous assessment was entirely justified by battlefield results. The M1 Garand was indeed among the greatest battle implements ever devised, not because it was perfect in every aspect, but because it fundamentally changed what was possible in infantry combat through elegant engineering. It proved that technology could multiply combat effectiveness more reliably than training alone ever could. It demonstrated that innovation beats mere refinement of existing technology. It showed that the future belongs to those who create genuinely new solutions, rather than endlessly perfecting old approaches to obsolete problems. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The British Lee Enfield remained an excellent rifle throughout its lengthy service life, spanning multiple conflicts. British soldiers used it effectively through World War II, Korea, and well into the 1950s with skill born of intensive training. It was reliable under harsh conditions, accurate at combat ranges, and remarkably fast for a bolt-action design thanks to its smooth action and 10-round magazine capacity. British riflemen trained in the Mad Minute drill achieved extraordinary proficiency with the weapon, but it was still fundamentally a bolt-action design, with all the inherent limitations that implied. No amount of intensive training could close the unbridgeable gap between manually working a bolt and letting the rifle cycle itself automatically through mechanical action. The American M1 Garand pointed unmistakably toward the future of infantry weapons worldwide. Semi-automatic operation became the new standard that all nations would eventually adopt. Within 2 decades of World War II's end, fully automatic assault rifles, firing intermediate cartridges, would become common throughout military forces globally. The days of bolt-action military rifles as primary infantry weapons were ending, and John Garand's revolutionary design hastened that inevitable end significantly. The comparison between these two rifles, the American M1 Garand and the German Kar 98K, encapsulates fundamentally different approaches to warfare that characterized American and German military philosophy throughout the 20th century. Britain and Germany relied heavily on professionalism, intensive training, military tradition, and tactical excellence to maximize the effectiveness of their forces within resource constraints. America relied systematically on technology, overwhelming industrial capacity, and continuous innovation to multiply the capabilities of average soldiers beyond what training alone could achieve. Both approaches had genuine merit in their contexts, but in World War II, American industrial might, combined with technological superiority, proved strategically decisive across all theaters of combat. The mathematical firepower advantage was stark and undeniable. While a skilled German soldier with a Kar-98K could sustain perhaps 12 to 15 aimed rounds per minute in realistic combat conditions, an American soldier with an M1 Garand could reliably deliver 40 aimed rounds per minute while maintaining better accuracy through consistent sight picture. In extended firefights lasting 3 to 5 minutes, this difference became absolutely overwhelming. A 10-man German rifle squad might deliver 600 to 900 aimed rounds in a 5-minute engagement if they maintained maximum fire rate throughout and weren't suppressed by incoming fire. A 10-man American rifle squad with M1 Garands could deliver 2,000 aimed rounds in the same 5-minute period while maintaining superior accuracy and tactical flexibility. This represented more than a 2-to-1 advantage in sustained firepower at the most fundamental infantry level. That disparity multiplied across companies, battalions, and entire divisions to create combat power differentials that German tactical excellence could not overcome through skill and courage alone. The human cost of this firepower imbalance appeared clearly in casualty statistics when controlled for other variables. While many factors affected casualty rates, including artillery, air power, armor support, tactical situation, and terrain advantages, careful studies of small unit infantry actions consistently showed American infantry inflicting disproportionate casualties in rifle firefights. The rifle each soldier carried made statistically measurable difference in survival and mission success. German casualties from American rifle fire were significant throughout the war across all theaters, and the M1 Garand deserved substantial credit for this documented lethality advantage. In final analysis, the M1 Garand's profound impact on World War II extended far beyond mere technical specifications or manufacturing statistics. It represented American industrial foresight in recognizing the need for superior infantry weapons years before war began. It demonstrated engineering excellence in creating a reliable, mass-producible semi-automatic rifle when most nations considered such weapons impractical for standard issue. It showed America's commitment to providing superior equipment to soldiers rather than relying solely on training and tactics to overcome technological disadvantages. While Germany struggled with overly complex semi-automatic rifle programs that never reached meaningful production numbers despite considerable engineering talent, America had equipped its entire multi-million-man military with proven, reliable semi-automatic rifles before entering the war. This staggering advantage multiplied across millions of individual soldiers and thousands upon thousands of separate engagements, contributed materially and measurably to Allied victory in both European and Pacific theaters. The distinctive sound of an M1 Garand firing, the sharp crack of 30-06 ammunition, the metallic clang of its en-bloc clip ejecting after the 8th round, the sight of American infantry advancing confidently with rifles at ready became synonymous with Allied victory throughout the war. German soldiers learned through painful experience to recognize and deeply respect that sound. They knew it meant they faced opponents who could deliver overwhelming sustained firepower quickly and accurately, without the vulnerable pauses inherent in bolt-action operation. The M1 Garand was indeed among the greatest battle implements ever devised by any nation, and its clear superiority over the Kar-98K was demonstrated conclusively on battlefields from 1941 through 1945, across every theater of the global conflict. The rifle didn't win the war alone, of course. Victory required successful combined arms operations, air superiority, naval dominance, overwhelming industrial production, effective logistics, and the extraordinary courage and sacrifice of millions of Allied soldiers, sailors, and airmen. But at the squad level, where soldiers actually fought, killed, and died in close combat, the M1 Garand provided a clear and measurable advantage that German infantry could not effectively counter with their bolt-action rifles, regardless of training quality or tactical skill. That fundamental advantage made decisive difference in countless engagements, saved countless American lives, and helped bring the war to swifter conclusion than might otherwise have occurred if American infantry had carried bolt-action rifles like their opponents. The M1 Garand stands as enduring testament to what properly designed, well-manufactured military equipment can achieve when fielded to competent soldiers. It proved that investing heavily in soldier capabilities and giving them the best possible tools pays enormous dividends in combat effectiveness and mission success. The rifle served the American military faithfully for over 2 decades, equipping soldiers in 3 major conflicts spanning World War II, Korea, and early Vietnam. Its fundamental design principles influenced subsequent rifle development continuously to the present day. For German infantry who faced it in combat throughout World War II, the M1 Garand represented an unpleasant but undeniable lesson in technological reality that shattered propaganda-driven assumptions. Superior equipment in skilled hands makes profound difference in the ultimate outcome of battle, a lesson paid for in blood on battlefields across Europe, North Africa, and the Pacific. The rifle's influence on post-war military thinking cannot be overstated. Nations worldwide recognized that the era of bolt-action infantry rifles had ended permanently. The Soviet Union developed the SKS and later the AK-47. Britain eventually adopted the FN-FAL. Germany's post-war Bundeswehr armed itself with the G3. Every major military force transitioned to self-loading rifles within 2 decades of World War II's end, validating the revolutionary path John Garand pioneered in the 1920s and 30s. Today, the M1 Garand enjoys robust following among collectors, competitive shooters, and military history enthusiasts worldwide. The Civilian Marksmanship Program, a federally chartered organization, has sold hundreds of thousands of surplus Garands to qualified American citizens since its establishment. Collectors prize M1 Garands as tangible pieces of history that changed warfare fundamentally. A rifle gifted to Senator John F. Kennedy sold for $149,500 in 2015. John Garand's personal rifle, serial number 1,000,000, sold for $287,500 in 2018. Original wartime rifles in good condition command premium prices in the collector market, reflecting their historical significance and the reverence in which they are held. The rifle remains popular at competitive shooting matches, where its accuracy and reliability continue impressing modern shooters 8 decades after its introduction. John Garand himself never profited financially from his world-changing invention, a fact that speaks to his character and the circumstances of his employment. He was a civil service employee earning $3,500 annually when he designed the rifle that would arm millions. He chose not to patent the design separately, allowing the government to own it outright for immediate production. After World War II ended, Congress debated granting him a special reward of $100,000 in recognition of his extraordinary contribution to victory. The legislation ultimately failed despite widespread support. Garand received various medals, citations, and honors from military and civilian organizations, but no financial compensation commensurate with his revolutionary contribution to military technology and Allied victory. He retired quietly from Springfield Armory in 1953 at age 65, having spent 34 years refining and continuously improving his rifle design. He lived peacefully in retirement until his death in 1974 at age 86, having witnessed his rifle serve American forces through 3 wars. By the time of his death, over 5 million M1 Garands had been produced by multiple manufacturers. His rifle had equipped American forces through World War II, Korea, and early Vietnam. His fundamental design principles informed every modern military rifle developed thereafter. The contrast with Germany's decision to retain the Kar-98K throughout World War II illuminates profoundly different national circumstances, strategic calculations, and military-industrial capabilities. Germany faced immediate existential threats throughout the war. Retooling factories to produce new rifle designs would have disrupted production for critical months, when every weapon was desperately needed at the front lines. Germany also faced global commitments across multiple theaters that America did not face until later in the conflict. German forces were scattered across occupied Europe, North Africa, and the vast Eastern Front. Standardizing on a revolutionary new rifle would require replacing weapons held by units on multiple continents under combat conditions, creating nightmarish logistical challenges. Furthermore, Germany's industrial capacity was substantially limited compared to America's continental-scale production capability. German factories operated under constant threat of Allied strategic bombing throughout the war. The combined bomber offensive destroyed factories, killed skilled workers, and catastrophically disrupted supply chains and transportation networks. Switching to a more complex, more expensive rifle design would have strained already overstressed manufacturing capacity beyond sustainable limits during total war. Germany made the calculated decision to continue with the proven Kar-98K and attempted to compensate through superior tactics, better crew-served weapons, and tactical excellence at small unit level. Germany did produce limited quantities of semi-automatic rifles. The Gewehr 41 entered service in 1941, but suffered reliability problems and complex manufacturing requirements. The improved Gewehr 43, introduced in 1943, was more reliable, but never achieved production numbers needed to replace the Kar-98K as standard issue. Germany also developed the revolutionary Sturmgewehr 44, the world's first true assault rifle firing an intermediate cartridge, but production began too late in the war to significantly impact outcomes. So Germany continued with the Kar-98K and made it work through superior training, tactical innovation, and doctrinal emphasis on machine guns for suppressive fire at squad level. German infantry achieved remarkable effectiveness with supposedly inferior individual weapons because they mastered those weapons completely through intensive training and integrated them skillfully into combined arms tactics. The mad-minute drill that made British riflemen so proficient had equivalent German training methods. But training and tactics could only compensate so far against fundamental technological disadvantages in sustained firefights. America faced entirely different strategic circumstances that permitted investment in revolutionary infantry weapons. Protected by vast oceans from direct attack, American factories operated at full capacity throughout the war without fear of strategic bombing raids. The nation's enormous continental industrial base could absorb the substantial costs of producing mechanically complex weapons at massive scale. America possessed the luxury of time before entering combat to develop and field advanced weapons. America could afford to equip every single infantryman with a semi-automatic rifle, because American industry could manufacture anything in virtually unlimited quantities given sufficient time and resources. This fundamental difference in strategic circumstances explains why America fielded overwhelming technological advantages in numerous areas beyond small arms alone. American forces had more trucks providing superior mobility, more radios enabling better coordination, more artillery delivering greater fire support, more aircraft providing air superiority, simply more of everything because American industry could produce everything in extraordinary abundance once fully mobilized for total war. The M1 Garand was merely one prominent example of how unmatched industrial capacity translated directly into decisive military effectiveness and technological superiority across all domains of warfare. The legacy of John Garand's invention endures in shooting ranges, museums, and private collections worldwide. Over 80 years after its initial introduction to service, M1 Garands remain extraordinarily popular among civilian shooters for their proven accuracy, legendary reliability, and profound historical significance as weapons that changed warfare fundamentally. The rifle represents the ultimate victory of innovation over tradition, of revolutionary thinking over incremental improvement, of American industrial might over resource-constrained opponents. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.